Okay guys, in this video we're going to be talking about rate laws, and so I'm going to show you what a rate law is and describe how it works, and then we'll use the rate laws to do some calculations, and then we'll also learn how to derive the rate laws from experimental data. So the rate of a reaction, as we've seen, can be expressed in terms of the change in concentration with respect to time for any reactant or product. But there's another way to express the rate of a reaction. You can express the rate of the reaction directly in terms of the concentrations without taking into account the changes in the concentration. Okay, so this is called the rate law. Let me show you. So we'll consider this first reaction of nitrogen dioxide and fluorine, and experimentally we are told that the doubling the concentration of the reactant NO2 doubles the reaction rate. Likewise, doubling the fluorine concentration also doubles the reaction rate. Okay, so what that means is that the rate of the reaction that we've been talking about can be expressed as a function of the reactant concentrations. Okay, and the information that we're given, if you double the NO2 concentration, the rate must double. That tells us that the rate is proportional to the NO2 concentration. The same thing is true for this statement right here, that the doubling the fluorine concentration doubles the rate means that the rate is proportional to the fluorine concentration. This proportionality factor K is called the rate constant. The reason it's called the rate constant is because it does not depend upon the concentrations of the reactants. Okay, I'll say it again, it's very important. The rate constant, K, does not depend upon the concentration of the reactants. That's why it's called the rate constant. Now later, we are going to find that the rate constant does depend upon temperature, but that's not the same thing as depending upon concentration. Okay, so this is an example of a rate law. If you increase the concentration of NO2, the rate of the reaction will increase. Likewise, if you do the same thing for fluorine, the concentration of the rate increases. So the rate law shows how the rate depends upon the concentration of the reactants. Now, you can have more complex rate laws than this one, but this is an example of a simple one. A little bit of the lingo, the term reaction order is used to characterize rate laws. The reaction order refers to the power to which the concentration of the reactants are taken. So in this generic reaction here, we've got species A, species B, perhaps a catalyst C, products D and E. The little a, b, d, and e, those are stoichiometric coefficients. Here is a generic rate law for this reaction. Okay? The terms, the powers M, N, and P are called reaction orders. They are often integer values. So for this particular reaction, we would say that the reaction is mth order with respect to reactant A. It would be nth order with respect to reaction B, and pth order with respect to C. Now, M, N, and P are usually integers, but certainly not always integers. We also talk about something called the overall reaction order, which would be a sum of the exponents themselves. So M, N, and P, you add them together, we'd say that the reaction is whatever this number is, order overall. So let's suppose this number was 3. We would say that the reaction would be third order overall. We'll go through some examples. I want to point out one very important fact. That is the reaction orders, the exponents in the rate law, they are not necessarily related to the stoichiometric coefficients. So in general, they are not the stoichiometric coefficients. Now, they might coincidentally match up with the stoichiometric coefficients, but it's just a coincidence. It's not the reason why. So the reaction order cannot be determined from the stoichiometric coefficients. They have to be determined experimentally. Okay, so you have to take experimental data to deduce what the reaction orders are. And I'll show you how to do that. Here we're just playing around with the definitions of reaction orders. So in this part A, we've got a reaction, and we're told that this reaction is second order in nitrogen dioxide and 0th order in carbon monoxide. Write the rate law. Rate will be equal to some rate constant. NO2, it's second order. Carbon monoxide, 0th order. Anything to the 0 power is just 1. So the conventional way to write this would be as K NO2 to the 2nd power and omit the carbon monoxide because it's not needed. For part B, we're given the rate law and they want to know what are the reaction orders. Well, we see that there's a 2 here for the nitrogen monoxide, so we'd say that it's second order with respect to NO, and it's going to be first order with respect to hydrogen. What would be the overall reaction order? 2 plus 1. We would say that it's third order overall. Now notice that the powers here numerically seem to be the same value as the stoichiometric coefficients. That's just a coincidence. Okay, you don't know that that's the case in general. Okay, so some experimentalists determined this. Just because the numbers match up doesn't mean that they're causal. Okay, here's another example. This reaction is first order with respect to methanol. It's 0th order with respect to the ethyl acetate. See, it's not present in the rate law, so it's 0th order. The overall order, first order. We're going to be using what's called the initial rate method to determine reaction orders from experimental data. What it consists of is a series of experiments where the initial concentration of one reactant is varied while keeping the other reactant concentrations fixed. Then you measure the initial rates and you compare the different experiments. There's a little table down here that can be useful. It says that if you double a reactant concentration and you find that the rate doubles, then it's first order. If you find that the rate doesn't increase, the reaction order is 0. If you find that the rate quadruples, then the reaction order would be 2. And we're going to go through some examples here right now. Okay, so we've got this reaction of nitrogen monoxide and ozone, and we're being asked to figure out from the set of experimental data here, what is the rate law? And so here is the generic rate law. So you're going to have some rate that's equal to a rate constant times the concentration of nitrogen monoxide times the concentration of ozone. And we need to figure out what are the reaction orders X and Y. And then they're going to want us to calculate K. Okay, so here's what you've got to do. You got to look at these different experiments and you got to figure out, I need an experiment where nitrogen monoxide is changing, but ozone is being kept fixed. If the ozone's being kept fixed, then any changes to the rate will be due to the changes in the nitrogen monoxide, and that's going to allow me to deduce what the value of X is. Then to get Y, I'm going to need to compare two experiments. Two experiments where ozone's concentration is changing, but the concentration of the NO is held fixed. For those two experiments, I'll be able to ignore the effect of the nitrogen monoxide, and then any changes in the rate will be due to the changes in the ozone. Okay, so let's see if we can piece through this. So let's try to calculate X. So we need two experiments where the nitrogen monoxide concentration is changing, but the ozone concentration is not. And so All right, you wouldn't compare 1 and 2 or 1 and 3. You might compare 1 and 4. Right? We see that the nitrogen monoxide concentration is doubling. And, too bad, the ozone concentration is increasing by a factor of 3. So we wouldn't want to compare those two. What about 2 and 4? No, that wouldn't work because the concentration of the ozone is increasing as well. So we don't want to use that one. How about 3 and 4? Right? You're doubling the nitrogen monoxide concentration. Look at that. The ozone concentration is fixed. Okay, so that's exactly what we want. So we're going to compare trials 3 and 4. And what do we find? We see that the rate, look, this is almost 2, that's almost 4. So we see that NO concentration doubles and rate doubles. I call this the eyeball method because we can just look at the numbers and estimate by how much they change. So we see that the rate doubles when we double the concentration of the nitrogen monoxide. So what does the value of x need to be in that case? Well, if x were 0, then you could make the nitrogen monoxide concentration anything you want and it wouldn't change the rate. If x is 1 and you double the nitrogen monoxide concentration, well then you're going to double the rate. Okay, so that's our conclusion. Therefore, x equals 1. Suppose that x had been 2. If x were 2 and you double the nitrogen monoxide concentration, well then the rate would quadruple. Okay, that's not what we observe, so we know that x isn't 2. Okay, so you double the concentration, the rate doubles, x equals 2. So we know one part of the rate law. Now we want to do y. We want to figure out what y is. So next we want trials where the nitrogen monoxide doesn't change, but the ozone concentration changes. 1 and 2 look good to me. Right? You're nicely doubling the ozone concentration, and the nitrogen monoxide concentration is fixed. Okay, so any change in the rate is due to the change in the nitrogen monoxide concentration. So we're going to compare trials 1 and 2. We see that the ozone concentration doubles. And what is the effect on the rate? So this is almost 6.5, and this, look at the exponent. Okay, this is a larger number than that. So this would be like 6.6. This is like 13.2. So we see that it's an almost doubling. So when you double the ozone concentration, the rate doubles. Same conclusion. This time y equals 1. So now we know that the rate is equal to K, nitrogen monoxide to the first power, ozone to the first power. To get the value of the rate constant, I can take any trial that I want to, and I just substitute that row into the expression. So K will be equal to the rate divided by NO times the ozone concentration. I'm just going to go ahead and take trial 1. So we've got 6.60 times 10 to the minus 5. That's moles per liter per second, divided by, we'll have 1.00 times 10 to the minus 6 moles per liter times 3.00 times 10 to the minus 6 moles per liter. And we can run these numbers through our calculator. And we're getting a big rate constant. That's okay. Sometimes they're big, sometimes they're small. Times 10 to the 3, 6, 7. What will the units be? We're going to have liters per mole per second. Okay, So this demonstrates the initial rate law method, initial rate method, and what I call this is the eyeball method, okay, which works very nicely when the concentrations double. However, not all problems are so nice, and so this will be an example of one where, let's see, no, is this one? This is one where they double as well. Is that right? Do I have a third example? Here's one. Yeah, so this one's similar. This one's actually easier because the rate for this problem here, the generic form of the rate law will be K times the concentration of this acetaldehyde to some power x. You need to find x and K. And you get a nice doubling of the concentrations here, or you could use this one where you get a nice doubling of the concentrations. Looks to me like the rate law quadruples, does it not? You go from 2 to 8 when you double the concentration of the reactant. So in this case, we see that the CH3CHO doubles and the rate quadruples. Therefore, x equals 2. And then you can find the rate constant K by rearranging this equation. Rate over CH3CHO squared, put in 2 for the x. You can plug in any trial you want and get the number for K. I'll let you do that as an exercise. I'm going to move on to this next problem here, which is a little bit more complicated due to the fact that the concentrations aren't evenly doubled. Okay, so we've got this reaction. The rate will be equal to some rate constant K times the nitrogen monoxide concentration to some power x times the concentration of the chlorine to the y. Okay, and so I need to find x and y. And so I'm looking through the trials and I see, okay, if I look at trials 1 and 3, we're increasing the concentration of the nitrogen monoxide, but it's not a nice doubling. And therefore, I really can't figure out what to make of the change in the rate. And so I'm going to have to use a more algorithmic approach to that. Here's how it works. For each trial, I can set for trial 1, rate 1 equals K times the NO concentration 1 times the chlorine concentration 1. Actually, I won't put a number there because it's the same in both. So I'll just leave it without a subscript. You can do the same thing for rate 2. Rate 2, K NO2 X Cl2 to the Y. Okay? You know, the problem is we've got 2 unknowns, 3 unknowns actually. And so we need to eliminate one of the unknowns in order to find them. And so what we'll do, I should have called it 3 for trial 3. So the subscript here, this is the subscript for trial 1 with these values for the concentrations and the rate. And then subscript 3, this is for trial 3 with these concentrations and this rate. Now notice that the chlorine concentration is the same in both of them. So what I'm going to do is a little algebra trick. I'm going to divide the top equation by the bottom one. You know, just like that. Okay, the rate constant is the same for both trials, and so that cancels out. The chlorine concentration is the same for both trials, and so that cancels out, leaving us with one unknown, x. How do we get the x out of there? Let me simplify it a little bit. We have NO1 divided by NO3 to the x power. How do we get the variable out of the exponent? We take a logarithm. I'm going to go with the natural log. Natural log of rate 1 over rate 2 will be equal to natural log of NO1 NO2 O3, sorry, and O3 outside. That's a little better. Okay, using the rules of logarithms, the x comes downstairs. Like so, and now I can solve for x. Natural log of the rates. Now we can plug in the numbers. So natural log of the first rate, 0.003 over 0.00675. Natural log of 0.10 divided by 0.15. We'll do the numerator and the denominator separately. So the numerator is giving me minus 0.8109. Denominator is giving me minus 0.405. 0.8 divided by 0.4 gives us 2. Here, I'll write it down here. Equals 2. So the minus signs cancel out. 0.8 divided by 0.4 equals 2. So this tells us that the reaction order with respect to nitrogen monoxide is going to be 2. We can do the same thing for the Y. Right? So here was our generic rate law. We've now found that x equals 2. How do we find y? We can do the same thing. Here we'll compare trials 1 and 2. Nitrogen monoxide isn't changing, but the concentration of the chlorine is changing. So we'll take a rate 1 divided by rate 2. Those terms cancel out because they're the same for both, and we get chlorine 1 over chlorine 2 to the y power. Do the same algebra, natural log of both sides. Rearrange. And plug in the numbers, so it'll be natural log of 0.003 divided by 0.0045 over natural log of 0.1 divided by 0.5. Again, we'll do them separately. So you get minus 0.4 here. Oh, it should be 1.5. 0.1 divided by 0.15 natural log. Let's see. 0.1 divided by 0.15 natural log minus 0.4 in the denominator, and so you get 1. So we've determined that the reaction is first order with respect to chlorine. So our rate law now is K, nitrogen monoxide, second order, chlorine, first order, third order overall. How would you determine K? You can take any of the trials and substitute the values in. You need to rearrange the expression like so. So you can take the values for any trial, plug them in, and that'll give you the rate constant. I'll leave that as a follow-up exercise for you. Here's another example. It looks like, to me, you will be able to use the eyeball method for this because it's doubling. The next section is kind of long, so I'm going to go ahead and stop this video right here.